Hello everyone, this is Stephen Massa with the Water Environment Federation. I want to welcome each of you to the CoMag and BioMag Systems Treating More with Existing Assets e-showcase. Before we begin, I would like to quickly review a few logistics. During this webcast, while you cannot speak directly to the presenters, you will have an opportunity to submit questions by typing your specific question into the GoToWebinar pane that appears on the right-hand side of your computer screen. We will be accumulating questions and will direct them to the presenters at the end. The PDF PowerPoint presentations are now available for downloading at WEF's website and are currently available in the Handouts pane of the GoToWebinar panel. This link will also be included in the follow-up email sent 24 hours after the webcast has ended. We will be recording this e-showcase. The recording link will be available on the webcast website 24 hours after the webcast has ended. PDH credits are not available for this event. Please note that today's event is an e-showcase and does not necessarily reflect the views of the Water Environment Federation. If you have any additional questions after the webcast has ended, please email webcasts@wef.org. Today's speakers are Jim Goodwin and Simon Radford. Jim is Evoqua's UK Applications Manager and Simon is Evoqua UK Sales Manager. Jim and Simon, I'll hand it over to you.
Thank you, Stephen. So welcome to our webinar on treating more with existing assets using Evoqua's unique BioMag and CoMag ballasted clarification technologies to both increase capacity and improve effluent quality. As you can see on the slide, we've included a brief resume of our careers. In summary, we're both graduate chemical engineers from way back in time before the existence of the internet, smartphones or social media. Yes, that bygone era of the 1980s. However, although we may appear ancient between us, we can boast some 60 years of joint experience in the separation technologies field of water treatment. I'd like to start by saying a few words on the Evoqua business. Evoqua is an international business that provides a large range of water treatment solutions. Mainly by acquisition, the Evoqua product portfolio consists of a number of wide-ranging water treatment technologies. Some of these technologies, like chlorine inspection, were established over 100 years ago, and others, like BioMag and CoMag, being more recent innovations. In Evoqua UK, there are around 140 employees who are involved in the supply of water and wastewater equipment to the UK, mainland Europe and the Middle East. Our Derby office is in the centre of operations for the supply of municipal projects. So what is ballasted clarification and how does it lead to such great benefits from a water treatment perspective? When you separate solids from water, there are two basic approaches. One way is to use some form of filtration barrier, such as a cloth or media. These work fine in the right application, but the biggest issue is that there is a limit to the quantity of solids on the filtration barrier before the need for removal by some form of backwash. As backwashing is not 100% efficient, they will also require some chemical cleaning to remove the impurities that are not removed in the backwashing. As such, this filtration barrier is potentially a real bottleneck that can lead to fouling, bypassing of the filter, and potential consent failure. So what if we could remove this filtration barrier bottleneck? This can be achieved by clarification. In this case, we separate the solids by simply using gravity to drop the solids out of the water in a clarifier. However, as the density of solids are almost identical to that of the water, you require a large surface area clarifier to allow the good separation to occur. Also, as there is no filtration barrier, fine material can readily escape out of the process. As a result of this, conventional clarification process does not normally achieve the quality of effluent that would be required with a filtration barrier. So the question is, what if we increase the density of the solids, allowing a much better separation of the solids from the water? By adding a ballast called Magnetite, this allows us to overcome the filter barrier bottleneck and the problem of slow settlement in clarification. This is the fundamental concept to both the CoMag and BioMag processes. So what can these processes achieve for the operator? Increase the capacity of your existing works. This approach relieves the traditional bottlenecks of your existing works to allow the user to treat significantly more load through the existing asset. Improve effluent quality. Meeting the regulations for better effluent quality is requiring significant investment in the UK water industry. In particular, to meet more rigorous phosphate limits. As ballasted settlement is now significantly better than conventional clarification, it results in truly excellent quality leaving the clarifier. Improve stability. The delicate balance of separating solids with similar density to water can easily be upset with a conventional solution. By making the solids heavier, the overall process is far more stable and robust to invariable solids and flows. Reduce footprint. As we can see with the case studies later on, we are reusing existing site assets and removing the need for new large civil tanks like ASPs or clarifiers. The equipment required to operate these plants are small and simple and occupy a fraction of the footprint of a conventional expansion. Capital cost. As you reuse existing assets, the capital cost for these projects can be highly competitive. This slide summarises the UK sites where we've employed CoMag and BioMag both in pilot trials, full-scale plant trials and in full-scale contracts. The first CoMag trial was performed at Packington, where Severn Trent Water were looking to test new technologies for phosphate removal. This led to a number of other trials, both pilot and full-scale. Later on in the webinar, we will be discussing some of these projects, with all having a common theme of maximising the use of the existing assets on their respective sites. Before we talk about the detail of the processes and the case studies, I wanted to discuss Magnetite and why it is such an effective ballast. Magnetite is a readily available product used in a vast number of applications. Its properties, such as high density and attraction to magnets, mean that it has unique benefits in all sorts of major manufacturing industries, such as steel or concrete. It is also used in everyday items like mobile phones and computers. Magnetite is a naturally occurring product which is fully oxidized iron ore that is mined all over the world. In Europe, it tends to be sourced in Scandinavia, but is used in such wide range of industries there is a plentiful supply from a number of different suppliers. In the case of water treatment applications, there are a number of unique properties of magnetite which make it ideal for ballasted clarification. It's fully inert. It does not react or chemically change. It does not rust or chemically degrade in the process or interfere with the biological or chemical treatment. High density. With a specific gravity of 5.2, it is over 5 times the density of water, and it is that allows the settlement of the solids to be so effective. Affinity to embed itself in the flock with gentle stirring, which results in the distribution of magnetite throughout the flock, as indicated in the picture. This is critical in that its ability to embed itself results in good separation of solids from water and leads to the excellent water quality produced. Magnetically retrievable. Magnetite is attracted to magnets, so this allows us to capture the magnetite escaping with the sludge and return it to the process. Non-abrasive. Magnetite is a talc-like solid that does not have any abrasive impact on the materials, such as pumps that it's in contact with. And inexpensive. It's not expensive to purchase at about 50 pence per kilogram. This results in a very small operating cost. So let's discuss the CoMag system first. What can it remove? CoMag is a chemical clarification process, so it can be used to remove the following list of contaminants. Although phosphorus exists in a soluble state, the addition of the coagulant, which is an inherent part of the CoMag process, results in the formation of a particle that will then settle out in the sludge. So, in summary, if it already exists as a particle or forms a particle as a result of the addition of a normal coagulant, then CoMag can be used to remove it from the water. Where is it applied? CoMag can be applied to any chemical precipitated clarification process. The main areas where it is currently applied are tertiary treatment, a distinct process step typically applied after the activated sludge process. We have a great example of a tertiary treatment application later when we discuss our Finham case study. Fixed film secondary clarification. In this case, we use the existing humus tank following a trickling filter as the CoMag clarifier. We will be discussing two examples of this later. In both of the above, in the UK, the aim is to improve the quality of the effluent, particularly for phosphate removal, where extremely low levels can be achieved. Industrial applications. CoMag is applicable to any chemical flocculation application, and a number are now used worldwide. One particularly valuable example is where CoMag is used for gold recovery. Also, CoMag can be used in other applications such as stormwater or drinking water treatment. Our US colleagues are just in the process of commissioning our first drinking water reference in Arizona. So how does the CoMag system work? The slide indicates a typical conventional clarification process with the addition of coagulant, some mixing and retention time, and some polymer then feeding a conventional clarifier. For CoMag, we introduce the magnetite ballast into the reaction tanks. We also have a recycle line which takes some of the magnetite infused sludge. This promotes solid liquid contact in the reaction tanks. This recycle is typically 10% of the feed flow. So the magnetite is circulating around between the reaction tanks and the clarifier. Although magnetite is inexpensive, we don't want to lose it in the waste sludge. So in order to recover the magnetite, we pass the waste sludge through the magnetite recovery system, which recovers the magnetite and puts it back into the process. Now we have the heavier magnetite infused particles. This allows us to operate at much greater settling rates. This means that we can treat significantly more through existing clarifiers, or if we are supplying a new clarifier, it can be 90 to 95% smaller. The recovery process at retrieving the magnetite is highly efficient with over 99.5% recovered. To compensate for the tiny losses, typically a few scoops of magnetite are added per day, or say 20 kilo bag every week. This slide shows a bit more detail of the process. Each reaction tank is sized for a roughly 3-minute average flow. The first two tanks simply provide retention time for the coagulant. it is tank 3 where we introduce magnetite, both from the recycle line and the recovered magnetite from the waste sludge. The recovery system consists of a shear mixer, which is like a blender that breaks down the solids, and it's immediately followed by a magnetite recovery drum, which uses magnets inside the drum to capture the magnetite from the waste sludge. As shown here, the magnetite recovery system literally sits on a platform above tank 3, so that the recovered magnetite is allowed to drop with gravity and a small amount of spray water back into the process. In tank 4, we add a small amount of polymer to capture any really fine material into the ballasted solids. This is a video that explains what's happening in each tank in more detail. I will then hand you over to Jim to talk about the CoMag case studies and to introduce you to the BioMag process.
This is the CoMag ballasted clarification process. It comprises a series of stirred reaction tanks which condition the water prior to it entering the clarifier, where the solids rapidly settle out to leave a very high quality, low turbidity treated effluent. The feed is pre-dosed with coagulant prior to entering the first reaction tank, from where it underflows to tank 2 and overflows to tank 3. At this point, magnetite is introduced, both in the recycled clarifier underflow, but also that recovered from the waste sludge stream via the shear mixer and mag drum at the top of the picture. This is a video we took in our 3 litres per second pilot plant, which at the time was treating raw sewage under storm conditions. Feed quality was approximately 150 milligrams per litre suspended solids. Tank 1 receives the raw feed, which has been pre-dosed with coagulant. It is gently stirred to allow the coagulation process to occur and flock formation to begin. The flow then passes to tank 2, where the flocculation process continues with more gentle stirring. If you look closely, you can just see the pin flock starting to form, as well as the other suspended solids from the influent. In tank 3, there is a lot more going on. Here, the recycled underflow from the clarifier is introduced, carrying a high concentration of magnetite. The magnetite adds weight to the flocks so they settle rapidly. Recovered magnetite from the waste sludge also re-enters the process at this point. In tank 4, polyelectrolyte is dosed. This firms up the flocks and mops up the fine solids and ties them into the flocks. From there, it flows to the clarifier, where it is allowed to settle. You can see this happening already. By way of comparison, we have taken a sample of the raw feed to the plant to demonstrate the relative qualities before and after the CoMag process. CoMag has been used in many applications, particularly phosphorus removal, but also in various other clarification processes, including stormwater treatment, drinking water treatment, and industrial process water treatment. I'm now going to introduce you to Finham, which will be the largest CoMag installation in the world when it goes into service. Finham Sewage Treatment Works is located near Coventry in the UK and is owned by Severn Trent. Its total phosphorus permit limit is due to be reduced to 0.22 milligrams per litre in March next year. The tertiary CoMag plant will therefore be required to achieve a total phosphorus level of less than 0.18 milligrams per litre and a total iron of less than 2. The other interesting figures on this slide are the maximum instantaneous flow rate through the tertiary system of 250,000 meters cubed a day. This next slide is an aerial view of the Finham site. On the right-hand side of the picture, you can see the 12 FSTs of the activated sludge plant, and to the left of them, the lanes. The entire output from the secondary treatment will then pass through the CoMag tertiary plant. You can see on this the two small blue circles and small rectangles gives you an idea of the scale and how the high flow is being treated in a very small footprint. The two CoMag tertiary clarifiers are each rated at 75% of maximum flow. So effectively, one CoMag clarifier of 21 meters diameter can treat the output from 9 32-meter clarifiers out of the activated sludge plant. Typically, CoMag clarifiers will run at 15 to 20 times the rise rate of a conventional clarifier. This next slide shows the layout of the CoMag plant at Finham. At the bottom, you can see the 12 reused RGF filter cells. We are using 4 of those as the CoMag reaction tanks. On the right-hand side, you can see the feed into the CoMag plant through 2 1,000 millimeter nominal bore pipes. From there, it passes through a static channel mixer and then into tank T1 and onwards through 2, 3, and 4. When it leaves T4, it passes in 2 1,300 millimeter diameter pipes to the 2 clarifiers. The overflow from the clarifiers then passes for discharge. The underflow from the clarifiers goes this way to the sludge pumps, which then return the underflow to the process. Most of it is a straight recycle, but a portion of it passes through the recovery process to remove the magnetite from the waste sludge. This slide is a close-up of the area around T3. This is the place where the magnetite is returned to the process from the underflow from the clarifiers. On the platform, you can see the magnetic drum separators, 2 of them. The shear mixers are close coupled onto those. So this is where the magnetite is removed from the waste sludge. The magnetite then drops back into T3. This disc behind is showing the sweep of the top entry mixers. There are 4 in that tank. Next to it, you can see the magnetite storage silo and next to that is the equipment for the automatic top-up of magnetite to make up for the very small amount of magnetite that's lost in the sludge. This next slide is a time-lapse video showing part of the tertiary clarifier construction and the peripheral launder being formed. It then swings around to show the reaction tanks being converted from filter cells into tanks, and the bridges and the top entry mixers going in. Now we're going to move on to a couple of much smaller CoMag installations in the UK. Again, the main driver for this conversion to CoMag was achieving low phosphorus. These sites are less than a tenth the size of Finham, yet they still offer the best combination of achieving low phosphorus levels reliably and at a competitive capital and operating cost. The total phosphorus permit at site B will be 0.25 milligrams per litre, similar to Finham. But as Simon mentioned earlier, CoMag has the ability to go down to much lower levels. And what this means is we're operating well within the process's comfort zone to achieve levels of 0.2. The other interesting thing about these two smaller sites is how they fit into the existing infrastructure. Where Finham is a standalone tertiary system with its own new clarifiers, these sites do it differently. This slide shows the existing process with the primary settlement tanks feeding the trickling filters, which in turn feed humus tanks, and they discharge to the environment. So instead of adding a tertiary CoMag plant on the back end, in this case, the CoMag equipment is slotted in between the biofilters and the humus tanks. This approach effectively retasks the humus tanks as CoMag clarifiers, meaning the only new tanks required are the small CoMag reaction tanks. And they have at maximum flow, they have a hydraulic retention time of about a minute each, to give you an idea of how small they are. No new clarifiers are required in this case. So briefly to summarize what CoMag offers. It has no physical barrier, which means it won't block up and it won't ever get into a situation where it can't take the required flow because it needs to backwash or something. While doing so, it can achieve ultra low total phosphorus, down as low as 0.05 milligrams per litre. It can be installed as a standalone tertiary process, or it can be inserted into the existing secondary treatment process, saving the cost of clarifiers. Lastly, either way, it only requires a very small amount of space to fit into, very small footprint. So that was CoMag. Now we're going to move on to BioMag. BioMag also uses magnetite to improve settlement, but that's where the similarity ends. BioMag is only applicable to activated sludge processes, but it can be applied to any type of activated sludge process. There's a list here, I won't read them out, but it can even be put onto SBRs. Let's now look at how the BioMag process works. On an activated sludge plant, clarifiers are the limiting factor, i.e. their ability to separate the solids from the liquid. Their performance places a limit on the solids concentration that can be used, i.e. the mixed liquor suspended solid. Typically that limit is not much above 3,000 milligrams per litre. This concentration effectively defines the size of the plant, or conversely, in a given plant, it limits the flows and loads a plant can treat. BioMag relieves this bottleneck by enhancing the performance of the clarifier. This small video is showing two samples of mixed liquor. On the left is conventional, and on the right is from a BioMag plant. You can tell that it's black from the magnetite. We set a stopwatch running, and the video will speed up shortly. There it goes. And you can see on the right-hand side, the BioMag sludge, or BioMag mixed liquor, has come down much more quickly. You can see better settlement and also a very clear supernatant compared with conventional mixed liquor on the left-hand side, where it's come down much less, and the top water or supernatant is murky. This reflects the level of solids which will come over the top in the clarifier. So this slide is a representation of a typical activated sludge plant, running at a flow of Q meters cubed per day, a mixed liquor of 3,000, and a clarifier rise rate or surface overflow rate of about 1 meter per hour. If we wanted to double the flow and therefore the load through the plant, a conventional approach would be to double up on the plant. If you want to double the flow, you need to double the tanks, double the clarifiers, double everything. If instead you were to convert your existing plant to BioMag, it would allow you to double the mixed liquor suspended solids level and also double the rise rate through the clarifier, through the FST. The result of that is you don't need the extra tanks. You can take that double flow and load within the existing infrastructure. Obviously, this doesn't completely come for free. The magnetite added to the process needs to be recovered from the SAS before discharge. So we have a magnetic drum separator. It's similar to the one used in CoMag, which separates the waste solids, the surface activated sludge, from the magnetite. The magnetite drops into a remix tank, which is also the same point that we add top-up magnetite to replace losses. At the same time, the final effluent quality is drastically improved with BioMag. This means that low phosphorus levels can be guaranteed directly from the secondary process. No tertiary system is required. With BioMag, we can guarantee TPs down as low as 0.02 milligrams per litre with no tertiary process required. I'm now going to hand back to Simon to talk about applications of BioMag.
Thanks, Jim. So the screen is showing the Severn Trent Rugby scheme, where Severn Trent Water were facing the combination of both requiring more treatment capacity as well as improved effluent quality. Due to the current performance of the plant, this future load increase would mean significant investment for a conventional expansion. Indeed, this investment would have consisted of 4 new settlement tanks, final settlement tanks. In addition, the conventional solution would also require upgrade and expansion of the existing deep bed sand filters. Whilst it appears relatively easy to put circles on a general arrangement drawing, this does not tell the complete picture. The ground at the plant is undulating, and so the hydraulics of putting final settlement tanks in the locations indicated would be complex and challenging. Whilst these 4 extra FSTs would solve the capacity problem, it would not solve the increased effluent quality that the plant needs to achieve. Therefore, as well as the extra FSTs, they would also need to refurbish and expand the existing sand filters to meet the more stringent effluent limits from the process. The alternative to this conventional approach was to maximise the performance of their existing final settlement tanks by introducing BioMag. Instead of the practical complexity of the conventional expansion, it is clear that the simpler solution for Rugby was to upgrade the plant with BioMag. For BioMag, all the magnetite recovery equipment required is housed in a building with a small footprint, as shown on the drawing. So, summarising the numbers for Rugby, the Rugby wastewater treatment plant, it's expected that it will need to treat more load, roughly 14%, to a population equivalent of just over 120,000 by 2028. The maximum flow is expected to increase by some 25%. The new effluent quality needs to meet limits of 0.32 milligrams per litre of total phosphate by the end of March 2020. How can we be confident that the BioMag solution proposed is going to meet those future challenges for the Rugby plant? This is a state point analysis that graphically shows what is happening in the Rugby final settlement tanks. Any regular clarifier designer will be familiar with these types of curves, as they graphically demonstrate the performance of a clarifier at different mixed liquor solids and flows. The green curve you can see indicates the current settling characteristics of the Rugby sludge in the existing FSTs. The intersection of the lines is where the current flow to full treatment, or FFT, sits within the existing final settlement tanks. As can be seen, this is outside of the current settling curve and therefore confirms what is being observed on the plant, which indicates that at the FFT condition, the final settlement tanks are struggling to cope, and this will result in the poor effluent quality leaving the final settlement tanks. Following solid settlement tests performed by Evoqua on the site, we can simulate how the settling curve improves dramatically by converting to BioMag. The addition of the magnetite improves the settlement characteristics of the Rugby sludge, thus allowing this huge increase in capacity to be easily accommodated within the existing final settlement tanks. So how will BioMag be introduced on the Rugby process to improve both the throughput challenges and quality. Here is the block diagram of the Rugby process, and the addition of BioMag is indicated. In simple terms, you can see that the BioMag process is a side stream process that takes the waste sludge from the final settlement tanks, recovers the magnetite, and simply returns it back into the biological tanks. This is a really straightforward additional process step that can be integrated without major disruption of the operating plant. When completed, the gradual introduction of magnetite during commissioning will then immediately improve the performance of the final settlement tanks. The equipment layout of the Rugby plant is indicated on the slide, with the building walls removed for clarity. To treat the full flow, the BioMag process will require 4 6-foot magnetite recovery drums. The magnetite is recovered through the shear mill, the 2 shear mills in this acoustically protected room, and the recovery drum combination. The recovered magnetite drops down into the remix tanks that I've removed the platform so you can see, where it is combined with sludge and returned back to the activated sludge process. The removal of magnetite from the sludge is very efficient, with over 95% recovered. These small losses are made up from the magnetite silo, storing magnetite and with a controlled addition to the process. The picture also indicates the frame of the building currently being put together on site. This is current progress. Evoqua are planning to commission the process in the autumn of this year. As a comparison, summarising the options available to meet the needs of Rugby, it was a choice of installing BioMag in this building or having to install 4 large 20-metre final settlement tanks. As a comparison of footprint alone, this represents roughly 20% of the conventional solution. So where is BioMag applicable? Capacity expansions. As we've seen with Rugby, significant capacity increases can be realised by adding BioMag to an existing process. Better quality. The quality of the effluent leaving the final settlement tanks is so good that a tertiary step is not required. Improves the settleability of the solids and allows capacity for storm flow. And as can be seen in the Rugby example, this is all possible in a very small footprint. So this completes the formal presentation slides. So let's look at some questions that the listeners may have that we've received while we've been talking.
Right, the first one, the question is, does the magnetite ballast impact on the alpha value on fine bubble aeration systems? And the answer, the short answer is no. Magnetite is added in approximately 1-to-1 ratio with the mixed liquor suspended solids. So if we're looking for, say, we're trying to achieve 6,000, there'll be another 6,000 of magnetite. So the total there would be 12. But the alpha factor wouldn't be as if you've got 12, it's as if you've only got 6. The magnetite embeds itself into the flocks and it's very dense and it simply doesn't get in the way. Next question, I'm just going to read this out. I'm interested in the guarantees Evoqua offer. What are the typical BioMag guarantees you provide with respect to BioMag SSVI and/or rate of hindered settlement, and 2, the guarantee with regards to the magnetite recovery system. So the first part, we would normally do a site test. It takes a couple of days where we do settlement tests similar to how you do an SSVI, and from that gather data and compare it with how the process performs with magnetite added. So we would, if this was for an upgrade, we would effectively create our new mixed liquor by diluting some RAS, do our jar tests, do our hindered settlement tests, and we would plot graphs like the ones Simon showed. But, from that, so we don't guarantee a specific SSVI, but we will guarantee performance of the clarifiers based on that data. We can guarantee the flow rate the clarifiers can take at a given mixed liquor suspended solids. The BioMag is effectively enabling the end user to run at higher mixed liquor suspended solids. The magnetite consumption is predicted within a range. It's not usual to guarantee it, but I think it probably could be if it was a requirement. With BioMag, we typically lose about 5% of the magnetite. So 5% of the SAS is magnetite. 95% is retained. Right, next question, I've just answered it. What proportion of magnetite is lost in the wasted sludge? How much top-up is required? See, we normally expect 95%. It can be under some circumstances as low as 90. So, but typically 95% is retained, 5% is lost. So that effectively is how much you have to top up. Next question, any issue of mixing in the aeration tank? For a well-designed activated sludge plant, you can convert it to BioMag without any issues, but it does make the solids settle better in the clarifier where we want it. In the aeration tanks, normal fine bubble aeration puts in enough energy to keep everything suspended. And obviously, as you'd expect, in areas where there's no aeration, in an anoxic zone or an anaerobic zone, you need to have effective mixing. But the bottom line is, it just needs to be working properly. It doesn't need to be significantly more than in a normal activated sludge plant. Another question, what is the maximum mixed liquor suspended solids that you can operate at? Well, this is going to depend on the quality and the state of the existing FSTs. So we can do the state point analysis to predict whether a clarifier will cope at a given flow. And as you'd expect, at the tough time for the clarifiers is at FFT, so that's where we have to consider it. Dependent upon that and that existing infrastructure and how far you're going to push the flow rate, we can go up to mixed liquors of 8 or even 10,000 milligrams per litre. And that's in addition to the magnetite, so you're talking about 16 to 20. That's an extreme case because most often the increase in load on a plant is not doubling or tripling, it's typically increasing by a few percent. On a plant where there's a big increase in flow, we do see jobs where there's a big increase in FFT combined with a relatively small increase in load. The conversion to BioMag will allow the clarifiers to run at these much higher rise rates. Next question. Does the addition of magnetite have any effect on dewatering of sludge or digesters? What we find here is it only ever makes it better, or it doesn't affect it. It doesn't make it worse in terms of dewatering. After the mixed liquor is shredded of its magnetite, it reforms flocks fairly quickly. And so we generally find it dewaters a bit better than before. We wouldn't recommend designing your sludge handling on the basis of getting better dewaterability, though. What we will say is it will never make it worse. And digesters, some of you will have noticed that magnetite is an iron-based compound. It's ferric oxide. However, it behaves purely as an inert. It doesn't affect the operation of digesters. Think of it as an inert, like a grit, except it's better than that because it doesn't all sink, because it's very, very fine particles. The magnetite that goes into the digesters tends to be carried out with the solids which are wasted from it. We have another question. What? I've lost it now. Sorry. They're coming in thick and fast. What are the advantages and disadvantages of BioMag over a granular activated sludge system? The first one, I would say, is you get much better quality directly from the secondary process. Granular activated sludge process needs to have a tertiary after it if you're shooting for a low P consent. Secondly, the ease of commissioning. BioMag is very easy to retrofit to an existing plant without shutting it down, without interfering with it. Whereas the GAC, the granular activated sludge process, you effectively need to build a new plant next to it. You need space to do that, and then basically abandon the existing old plant. And the BioMag is very easy to commission. It's a question of wet commissioning, running the recovery system on water. Then you can start running your normal SAS through the BioMag plant, and then you can start adding the magnetite and building that up to allow you to then increase your mixed liquor solids if you need to, and also to get the benefit of the higher effluent quality. Next question, do you have any operating example of industrial applications for CoMag? We have several, not in the UK. We have one in Ireland. I can't publish the name of the end user. As I mentioned, there's a gold mine in America which uses the CoMag process.
The one in Ireland, Jim, that's the one that recovers calcium fluoride. So that's used to basically recover it's an industrial process which uses fluoric acid, and they recover the calcium fluoride rather than putting it down a waste. And the reason and the driver for that was that they were trying to fit it in a really tight area, so it was a minimum footprint issue, and they saw CoMag as the only way that could achieve that. So it was the driver there was the quality and the low footprint.
Another one, what is the concentration of magnetite in the system, i.e. the mixed liquor suspended solids? I think we've covered that earlier, but I'll reiterate, we typically add approximately 0.5 to 1 times as much as the mixed liquor. So if you wanted to run a mixed liquor of, say, 6,000, you would add 3 to 6,000 of magnetite to that. We have a question about, is there a risk of septic conditions, for example, in a sludge tank, resulting in reduction and solubilization of iron from the magnetite We haven't seen this. It is very stable oxide of iron. It's not hydroxide. I think if you got to very, very low pH, acidic conditions, ultimately an oxide will react with an acid to produce a salt. But I think that would be extreme, and we haven't seen that happen.
So I've got one here, Jim. So somebody's come in and asked, do we have a trial plant so I can prove the technology, and how much would it cost?
We've got a pilot plant for CoMag. We haven't got one for BioMag because it's inherently difficult to trial. You have to convert at least, you have to convert the whole process, or at least one section of the activated sludge plant. We have a CoMag trial plant. It'll run it up to 3 litres a second. It can be used for any type of oil. So we've done a stormwater trial. We've done a tertiary trial. We've done an industrial trial so far. So that is available to rent.
I think with BioMag, what we do is, instead of having a trial plant as such, as we've sort of indicated on the presentation, we recommend the use of the solids flux test to prove the settlement. That really does make it really demonstrates how the settlement will improve over the range of sludges that will be experienced. So we have a test rig for that, and that would typically take a week, a day to set up, a few days trial work, and then a day to take it away. And that would that's then we generate a report, and that is sent to the customer to see how the benefit of BioMag would work on that particular site.
And that's a very good predictor of BioMag performance, even if it's a stirred settlement test. We've shown it gives very repeatable results. Another question: how would the increased settling velocity may affect solid settlement in the pipework? We cover this just by running minimum velocities. So we found that a specific velocity in CoMag, which is a harder one to deal with, it has the higher magnetite particle sizes, and we're running at a higher ratio of magnetite to other solids. We find if solids get it, if the velocity is taken above a magic number, it will pick up any solids which might have settled. So it means we can run at lower velocities for limited times, provided the flow rate gets back up above the level to pick them up again. In BioMag, the settlement is less of an issue. It's smaller particles, and they are quite slow to settle on their own.
Okay, well, we're getting close to running out of time, so I think I can take maybe one more. Just looking down, Jim.
We've got a question: any issue with existing clarifier scrapers? Similar to what we say in terms of mixing to avoid settlement in the aeration tanks. If the scrapers and clarifiers are in reasonable condition in the first place, converting to BioMag is not going to be a challenge to them. If they are ropey and on their last legs, it may struggle.
Okay, I think we can take one more, and then I think what we'll do is we'll bring it to a close. We will any questions we've missed, we can put a question and answer sheet too, and we'll send that out to everybody that's attended the webinar. So if we don't get round to your question, then we'll reply by email, and if there's more than interaction required, then you can always get in touch with us. So do you want to say the last one? The last one we've got here, Jim, is can the process operate 24 hours with only being manned 8 hours a day?
Well, I'd answer to that it doesn't really need to be manned even for 8 hours. It's a fully automatic process. The only intervention that's required on smaller plants is topping up the magnetite, which needs to be done only once or twice a week, because it's not a dosed reagent that needs to go in continuously. It just needs to be topped up intermittently.
Okay, I think we're about done. We've run out of time. We're a minute over, so I think we might get in a big trouble with the WEF organisation if we carry on talking.
No, that's all right, guys. Thank you very much, Simon and Jim, for your presentation today, and thank you to our audience for listening in with us. As Simon and Jim mentioned, we will provide a list of all the questions that were asked to them, and any that we didn't get to cover today will be can be responded to directly. We will also, just a reminder, be sending out a follow-up email 24 hours from now that will include a link to the webcast recording for anybody that would like to watch it later, and we'll also include a link to the copy of the PDF presentation handouts for anybody that would like a copy of those as well. So thank you all very much for attending, and we hope to see you at our next webcast event.